we are able to measure 8 alpha. I'm color coding on the left with the density, on the right, on the middle, sorry, with the redshift. So you see that there is no bias in relation with the redshift. So that's good. We can measure 8 alpha up to redshift 0.35. That is the limit at which 8 alpha goes outside of the J-PAS range. And well, this is for 8 beta. And here we have the result for oxygen 3 and nitrogen 2. Those lines are more difficult to constrain actually. And you see here that there is if you look at oxygen 3 line, there is a branch where we are under predicting the equivalent width of oxygen 3. And this applies as well to nitrogen 2 line. So at the same time, from 50 Armstrong or so, we start to under predicting the equivalent width, but we are not doing as bad. So if we look now at the ratios of those lines, you see that in some region we are able to retrieve the nitrogen to 8 alpha ratio, but then again at a certain point this start to so we start to under predict a little bit the ratio. That has an explanation that I will tell you in a second. And when it comes to oxygen-3 and 8 beta ratio, that happens as well. At high values, there is a little bit of a flattening. So if we plot that in a BPT diagram, this couple of ratios, on the y-axis, oxygen-3 to 8 beta, on the x-axis, nitrogen to 8 alpha. Those are, on the right, we have the Sloan BPT diagram that comes from the spectrum directly. So those are measurements in the spectra. And this is how it's the BPT diagram. On the left is what we predict training with Khalifa and Manga galaxies. So what you see that the network has more problems in regions where the main ionization mechanism is driven by active galaxy nuclei. So this happened mainly because as we are training with galaxies in different zones, the number of zones that are in the middle and that has as well an AGNs are few compared to the total amount of spectrum that we are using in the training. So at the end of the day, it has more difficulties to train to predict in this region of the BPT diagram. So I want to show you here. This is if we had trained the network with a Sloan, and then we predict in a Sloan, you see that things are much better, right? And you can think, okay, that's all, right? If we are able to do it, why we should care about CALMA, about Khalifa or Manga? The story is that if you are if you stop here and you are satisfied with this performance, this is here the calibration and everything is the same between these two surveys. So that's not guarantee you that when you go to other galaxies, other experiments, you will be able to reproduce as well this diagram. I don't have here the plots. Maybe I can show you later. But if we train with a Sloan and then look at how it's performing Khalifa or Manga, we have other problems that are not related with the AGN branch, but with the star formation sequence. Okay, so let me talk now a little bit about the uncertainty we have in our predictions. So this is an J-PAS spectrum that has been perturbed according to the signal-to-noise ratio that we have in the photometry. So imagine we have a signal-to-noise ratio of 10. We move these fluxes according to this error, and we make a, let's say, 100 prediction, so you have an idea of the uncertainty you have in these lines. Here, the signal to noise ratio that we can measure in the line, this in the y-axis, is a function of the signal to noise ratio that you can measure that we have in the photometry. They are related, right? And but there is another variable here that is the equivalent width of the line. For lines that have a high equivalent width, with less signal to noise rate in the photometry, we still can measure them. But as lines are weaker, they are more difficult to measure. So if we put that in words, for a line that has an equivalent width of 10 armstrong, let's say, if we want to measure H alpha, that is the plot on the right, we have to have at least a signal to noise ratio of the photometry of 4. So if the signal to noise rate is below this value, we can no longer measure H alpha for an equivalent width of 10 armstrong. Okay. And here I'm comparing this method, that is the method based on machine learning, with what we would be able to do if we, instead of using this method, we use something more traditional, that is based on the photometric contrast. So basically, you measure the line in the filter that take most of the flux, and then you measure the continuum, and you make the difference. So that's the contrast. And this red line here is the how the signal to noise ratio in this line is related with the signal to noise rate in the photometry. So basically, we can do it much better that what could be done using other methods. This work has already been published, and now the idea is to use this methodology to exploit the data in the ages field. So this is what I'm going to talk now. So as I said, we have 4,000 objects in the miniJPAS area. So we are interested only in galaxies. So among these objects, we select the ones that are galaxies. We put a constraint in the redshift. We don't want galaxies to have a redshift higher than 0.35. And also we put a limit in the R band, in the magnitude of the R band. So this is our sample. We have roughly 2,300 objects. And you see there the relation between the magnitude and the photometric redshift. Here there are again more samples of galaxies in J-PAS. You see also the image in the R band, and the emission lines are clearly visible in most of them. So the idea is to measure them with this method. So one of the first thing we look at was these color mass diagrams. So here what we are showing is the U minus R intrinsic color of the galaxy in function of the stellar mass. And on the right, galaxies are color coded with the luminosity H. And on the left, they are color coded with the equivalent width of H alpha that we retrieve using this method. So what we are obtaining is something expected. There has been many works that has already looked at these diagrams and have obtained similar results that are basically red galaxies that has colors that are redder. They are more massive in average. They are also older. And if you look at the equivalent width of H alpha, they have low values, so mainly they don't have emission lines, right? As galaxies get younger, they have they don't have they have higher emission lines, and they are less massive. Okay, so here we have a couple of diagrams, the BPT diagram that I already have spoken about. And so here, first of all, I'm both diagrams. I will talk later about the hand diagram, that is the one on the right. But both diagrams are color coded with the mass of the galaxy, with the stellar mass. And we are imposing that for a galaxy to appear in this diagram, we impose to have an error in both variables lower than 0.25 dex. If it's higher, it doesn't appear. Okay. So among all the galaxies we have in the AG field, there are 255 that goes in the BPT, and you see how the star formation WHAN, that is the part that goes from high values of oxygen-3 to H beta to low values of nitrogen to H alpha. So this is a sequence actually. So galaxies start to have start with low mass, and then as they become more massive, they become more metal rich, and also they have less emission in less amount of emission lines. So you see that something that comes from the emission lines from this method, and other variables such as the mass that comes from the set fitting, they are compatible here, and tells the same story. If we look now at the hand diagram, that is the one on the right, here we are showing the equivalent width of H alpha in function of the nitrogen to H alpha ratio. So here we only need 2 lines, we don't need 4. And so that means that we can place more galaxies in this diagram, because the error in the y-axis is in average lower. And also, since oxygen-3 is the line that is more difficult to obtain, we can benefit for removing this line and using only this diagram. And again, here in this diagram, galaxies that are star forming, they lie on the left, and as they become more massive, they go to the right. So you can use this diagram to separate between star forming galaxies, safer, and other species as linear, passive, or composite. So since this is less costly and we can place more galaxies in this diagram, we use that one to make a selection of star forming and try to measure the star formation rate for those galaxies. In order to measure the star formation rate in the galaxy, first we need to get rid of, to make an estimation, of the amount of interstellar gas that is absorbing part of the emission in the flux of H alpha. So since we have H alpha and H beta line, we can compute its ratio, and from there we can obtain the color excess, and therefore the amount of nebular dust extinction at H alpha wavelength. So what I'm showing here, it's among all the galaxies that are star forming, I'm showing the relation between this nebular extinction and the stellar mass. The dot points are median values or in ranges of in stellar mass beams, and I'm comparing this with other studies. We see in gray the contours that has been derived from our work done by Salvador in 2016. Those come from Sloan galaxies, and they have used aperture correction to estimate the ratio of H alpha and H beta. As you remember, maybe Sloan has a fiber of 3 arc seconds. So that means that the galaxies that are in the nearby universe Sloan only observed the central part. So if you want to know all the flux that come from the whole galaxy, you need to apply aperture correction, and this is what Salvador did. And there is also another line that's come from another study with Sloan galaxies as well, but they don't use aperture correction. So you see that there is a difference in terms of using this aperture correction or not using it. And the good point of J-PAS is precisely that, right? We are not, we don't have a fiber. We can observe the whole galaxy, so we are not biased in this regard. And finally, other points that are there comes from a cluster at 0.4 from Sobral in 2016. And well, we are obtaining similar results. So we use this nebular extinction to remove, to add the contribution of, to have finally the H alpha flux, right? And from there, using the Kennigat conversion, we can estimate the star formation rates that each galaxy in the star formation sample has. And since we also have the stellar mass, we can derive this star formation main sequence. And so here we are plotting the, we are color coding this graph with a parameter that is tau divided by T0. So that comes from the star formation history. In the set fitting, we assume a delta delay model. And T0 is basically the starting point of when the galaxy starts to form a star. And tau is how extended the star formation is in the galaxy. So by dividing these two quantities, we have an idea of whether galaxies are still forming a star or its star formation has started to decrease. And what we observe again is that the galaxies that are above the main sequence, above the main fit here, they are more active in terms of star formation. And the galaxies that are on the lower part, they are less active. So again, you see that one of the aim of this work is to use different tools, something that's come from the stellar population, from the set fitting, and something that's come from the emission lines that in principle, so this method are independent from each other. And we have tried to put everything together and find consistent result. And this is again proving that. What we obtain is a slope of 0.9, and we have also retrieved the amount of intrinsic scatter, and this is 0.2. For this fit, we have taken into account, of course, the errors, both in the star formation rate and the stellar mass. Here I'm showing how this slope compare with other works. We have in empty symbols comes from simulation that predict a slope of the star formation main sequence from 0.87 or so up to a superlinear slope. And the other points that are not empty, those come from experiments. Our result is the blue one. You see here there is a gray point on the top. This comes from Sloan, and it's the same work of Salvador that use aperture correction. And there is a debate of how this aperture correction can affect actually the slope of the star formation main sequence. The gray points comes all from Sloan, so there are other points here that are on the low part that fit the star formation main sequence Sloan and obtain lower results. In principle, this aperture correction can affect. So with J-PAS, we don't have this problem, and what we are obtaining is something that goes more in this line. Okay. This is just this is the last plot I'm going to show. This is the cosmic star formation rate density. Since we have the star formation rate for all the star forming galaxies, and we can compute the volume at different redshift bin, we can finally obtain this quantity, the star formation rate density. Here we are comparing, there are many dots there. You see everything that is in gray, that come from studies that use H alpha to retrieve this cosmic star formation rate. And the other lines there that are in color, that are studies that obtain this quantity with information of the stellar population. So in general, there is a bias between these two methods, and we are also obtaining that. So our predictions are a little bit lower compared to what stellar population model had retrieved. In particular, the black dots there, those are the values obtained with the same galaxies that we are using here, but with the method of the set of the seed fitting. And well, there are several hypotheses of why this is happening, and maybe actually this is a combination of several factors. We could be underestimating the nebular excitation. This is a possibility. There are also a fraction of H alpha photon that can escape the nebula, and we are not taking into account that in our recipes for converting to H alpha to star formation rate. And it can happen as well that the models that retrieve the star formation rate density with a stellar population overestimate the amount of younger stellar population, or even the single stellar population models that predict the amount of ionizing photons are overestimating its prediction. So yeah, this is what we have obtained, and this has been all this plot that I've showed you are part of a paper that is going to be sent in few weeks to Astronomy and Astrophysics. We hope will soon be available for everyone. And just I will move to the conclusion and the outlook for J-PAS. We have a survey that will scan an unprecedented volume in the sky, around 8,000 degrees square, with a very low resolution spectrograph. So just doing little numbers with this 1 degree square in the edges field, that means that at the end of J-PAS, we will be able to obtain the main ionization mechanism for 2 million galaxies in the universe. We will retrieve the main sequence for 9 million galaxies. And we can also study the spatial distribution of galaxies, because J-PAS will observe galaxies that are nearby, and we can divide the galaxy in zones and look at the individual regions and use this method for that. And just this work, this machine learning method is just a starting point of other application that we can imagine. For instance, try to measure the oxygen to line that is in the H, in the ultraviolet region, and use that as a tracer for measuring the star formation rate. And well, we can also use the images for training a network. For now, we only use spectrum, pseudo spectrum, but we're going to use also images and try to do more advanced classification of galaxies in terms of morphology, nuclear activity, etc. So I will leave it there. Thank you so much for your attention, and it's time for question.
So thank you very much, Ines, for this talk. And now the talk is open for questions for the people that are here at the hall. If you bring your own microphone, yes, you can make your question with your mobile. And the people in Zoom, I can see one question here. Please, Mohamed. Yes. Yes, we can hear you.
No.
Mohammed, we cannot.
Do you hear me now? Sorry. Yes. Okay. Sorry. So the photo Z is right now an input to the method, because if I understood properly, right?
That's right, Mohammed. That's right.
Yes. So have you studied the error in the photo Z and how that may affect the final estimation, similar to the nice work you did on estimating the error of the photometry in each of the bands?
Yeah, that's a good question. I didn't mention that, but actually, what the network does is it takes the photometric estimation, and also it takes its error to compute in all the redshift within the error. It computed the equivalent width of those lines, right? So then you have for each galaxy you have 100 prediction for due to the signal to noise rate of the photometry, but you have also a prediction for in each redshift beam. So then there is a kind of average there, and also there is a way of how to say that the network. So in each redshift beam, we compute the equivalent width, and then there is a way to look at the redshift that provides the highest sum of the equivalent width, because this correlates with the best redshift.
Exactly.
I should have had this plot in the presentation to make it more clear. But if you look at the paper, at the first one, that is already published, you will see there a better explanation of what I'm talking about.
Okay, thank you very much.
So thank you, Mohammed. Then we have a question by Pepa Josefa Macegosa. Please go on.
Thank you, Ines. I enjoy very much your seminar, and as I have been working, trying to get the result from Alhambra long ago, and so that I appreciate very much the effort you are doing getting emission line object from J-PAS. I have a question related with Mohammed asked already, that you are working with galaxies that you already know the redshift. Am I right?
Yeah, the photometric redshift.
Okay. So no, because I wonder when you do the exercise blindly in the survey, and you don't know, you don't have any idea, a priori idea of the redshift.
Yeah. Okay. Let me show the plot that will make it clear.
So I would like to know that if you do so, how can you play with this?
So
can you constrain the redshift in that way, or how do you proceed with that? Because this is
yeah. So basically, here in the when we did the simulation, we thought about that. We know that the redshift will have an uncertainty, so we explore how if we input galaxy that has an error in the redshift, how well we could retrieve the equivalent width, and here are the results. So the thing is that we thought about a method to correct if somehow the redshift is not well estimated, and this method is based in the sum of the equivalent width. So in each redshift beam, you make your prediction, and then you sum all over your equivalent width. And what happened is that the right redshift coincides with the highest sum in the equivalent width. So we have somehow a way to correct if the redshift is not provided well. And here there are the simulation we did with an error of 0.01. We still can't measure H alpha. We of course higher the error in the redshift, the more difficult it is to obtain the prediction, but still we can do a good job.
Okay, and I have another question. Is how do you get rid of the quasars and type 1 in your system?
Well, in the selection that in the sample selection that we did at the beginning, we imposed to have extended sources. So that comes from the extractor that compute. Well, there are other methods, but here in this work we use the output of the extractor, and that gives us the stellarity, or whether galaxies are extended or point sources. So we get rid of point sources. So we will not have quasars, or at least very few quasars in the sample. But we'll have a safer 2 galaxy, that's for sure.
But the safer
safer one.
Yeah, in principle, it seemed to me very difficult to distinguish with in these photometric surveys if the line is broad or is narrow.
Yeah, so the thing is, if those objects are extended sources, they will be here for sure. And then the way of getting rid of this object is based on the hand diagram or the BPT. This is the only thing we can do.
No, but the BPT diagram doesn't have any meaning if in type 1 sources, because if the Balmer line are broad, it can be located in any place of the BPT diagram. So the question is that maybe it's interesting to look at if we can distinguish between broad lines and narrow lines.
Yeah. So yeah, that would be a good thing to look at. For the moment, as I said, is the stellarity what we are looking at. If the galaxy is extended and this is still a safer one, that will be in our sample contaminating. So, but yeah, maybe this is.
Well, I suppose the contamination is pretty low, because if you take any complete survey, the percentage of type 1 CFE would be few percent, so that I suppose the contamination is pretty low. But it is nice to look at, and I suppose because in J-PAS there is a group working in quasar, and they are working on that topic as well. So
yeah, there are other works that are trying to separate between quasars at low redshift quasar, but they don't make distinction between safer one or quasars. So, but I think at some point whenever we have many more data of J-PAS, it could be a good idea to use the images to maybe train a machine to separate between this type of galaxies. But yet for the moment, this is what we have. And as you said, maybe the contamination is not as high.
No. I'm pretty sure that this is not hard. Thank you.
You're welcome.
May I do a comment to Pepa?
Sure.
Question is that in fact it has been recently demonstrated by other collaborators that in fact the quasars are very nice detected in the J-PAS, and also they can measure even the full width and maximum of the emission line. So that means that obviously it depends a lot of the line, the strength of the emission line to be detected or not. But I mean that with J-PAS, thanks to the resolution that we have with the filter, it is possible to clearly detected the broad emission line and even to measure the full Wiham maximum of this line. And also there is another, I don't know why, but Ginés didn't present it, but even he is also working in this kind of analysis using machine learning to retrieve or to the quasar that it is available in the, well, that it is in the miniJPAS using also machine learning. And the other thing is that there obviously could be some cipher 1, cipher 2 line where the stellarity could be not equivalent to a point source, and in that case it will be probably in our sample. But in any case, we put a lot very strong constraint into the stellarity, which is 0.1, while it is the source quasar will be around 1. So that means that we are putting a strong constraint to the stellarity to exclude most of the AGNs and quasar objects. And we didn't find any, when we analyzed the continuum, we didn't find any that could be that couldn't be fit with the stellar population model. So that means that if there is someone the continuum list, it is not dominated by the quasar or the AGN line at the optical wavelength.
Okay, thank you very much for the comments and the questions. Here at the room, any questions? No question here. Good. Okay. Another opportunity in the Zoom. Okay, I see no questions. Thank you, Ginés, for this talk. And we will come back next week with the next seminar. Thank you very much.